I'll go ahead and jump right in, and I want to start by saying that, and making clear that what I'm talking about today is definitely not my own ideas in any way, and I want to acknowledge there's really a rich literature on this question of how to use climate impacts data to assess impacts of climate change and also to affect decisions ultimately. Okay, so just to set the stage, what am I talking about here? There, especially in recent years, have been a whole bunch of climate impacts data sets that have come out. And the question really is, how do we choose among these? How do we evaluate them relative to one another? What exactly do we use in any particular situation? And I want to start with just sort of hopefully a review of what the typical approach is for putting these together. So typically we start with, here on the left, the climate projections. And the climate projections are not just projections from global models, but also scenarios for emissions or pathways of greenhouse gases through the 21st century, and often involve multiple simulations, even from single models. Okay, so we take those, and those are at a low resolution. So commonly they get downscaled from the low resolution of the models, which is about 100 to 200 kilometers spatial resolution, to medium or small scales that are more relevant to some of the decisions that we're looking at. Right. Another common step after that is to take that downscaled data and run it through an impacts model. And a hydrologic model is one example, vegetation modeling. We heard just now about some species models. Any sort of impacts, translating from climate changes to impacts of interest. Okay, so that's a typical approach. One of the big concerns there is that we're starting, as we go from large-scale changes from the global models to increasing specificity in terms of scale and in terms of variables, the question is really, what is that doing in terms of uncertainty? We have models with uncertainties at each step of the way. They're compounding. How do we contend with that uncertainty? How do we quantify it? How does that affect our decisions? Okay, so that's sort of the basic problem that I'm starting with here with this talk, which is we've got lots of data sets, which is admittedly a kind of a good problem to have, but how do we choose among them? And how do we contend with uncertainty? So ultimately, this is sort of a schematic of what I sort of imagine is what you want when you're thinking about climate impacts or how to make a particular decision that might be affected by climate change, right? So I've intentionally left these axes unreadable because it could be really climate change for variable X and variable Y, and thinking about how that projects onto the thing that we're interested in. So in this case, I'm showing a contour line, say maybe some threshold of change that affects what decision we make, right? And you can imagine looking at what the climate projections say about that and how they fall either on one side or another of that line. Just to be a little bit more concrete about that, here's one example from a paper from Southeast England where they were interested in assessing the risk of a 20% increase in peak flood events. So that's what these contour lines are showing. They're the percent increase in peak floods, and it's shown against changes in the seasonality of precipitation versus changes in total annual precipitation, right? And then they've got these contour lines that they've developed, and then they look at where the projections fall on that map. So there are real 2 points here. One is that the real work here isn't so much in developing the climate data sets, but at figuring out how to use them, right? That's these contour lines here and here. The real work is doing the sensitivity study, figuring out the information needs, and then the next step after that is to figure out how best to satisfy those information needs with the projections that are out there. So I thought this was summarized in a different way, in a nice way, in a webinar I listened to a few weeks ago by Lynn Helbrecht at Washington Department of Fish and Wildlife. And she was summarizing sort of their lessons from thinking about how to incorporate climate change into their decision-making over the past few years. And really her points really boil down to this idea that we've got this sort of top-down approach where we've got these climate models giving global projections, we've downscaled them and run them through models. We need to combine that with a bottom-up approach, right, where we've assessed the sensitivities and the information needs and figure out where the nexus is between the two. There's a paper coming out this year by Amy Snover at SIG and a few other people where they've really attempted to lay out some of the concrete considerations. You know, once we've sort of come to this conclusion that bottom-up assessment is needed to inform decisions, what are actually some of the specific decisions that we need to make about our needs and our decision context in order to think about what we need from the climate projections, right? So they break it down into 3 steps: developing a conceptual model of the system of interest, so its sensitivity to climate change, and quantifying that. And what that tells you really is what climate variables or what variables we're interested in. The second step is the sort of climate science piece. How does climate affect the system of interest? How are those sensitivities impacted by climate? Are we able to simulate it, and at what scale, temporally and spatially? And what that tells us is what sort of data we need. So in each case, we have sort of an information criteria and a choice in terms of using the data. And finally, the decision context. Are we risk tolerant? Are we risk averse? What are the timescales for this decision? What that tells us is how to cull the list from the sort of hundreds of scenarios that are available to a smaller set that's more manageable for analysis. Right, so I'm going to spend the rest of my talk just sort of walking through some of these and giving some examples of the concrete considerations. Okay, so the first one, choosing scenarios, right? And this is really about quantifying sensitivities to climate. So here's a qualitative example. You can imagine thinking about salmon throughout their life cycle and how they're affected potentially by climate change. So flooding in early stages of life, changing timing of flows for the smolts and juveniles, warm, low summer stream flows for salmon trying to swim upstream to spawn. And ultimately what we would want to do then is go back to this idea of quantifying it. What we basically want to do is be able to place contour lines, against changes in climate-related variables in order to assess the sensitivity to climate change, right? So again, there's a lot of work in here, and it's actually not really related to the climate data sets itself. It's sort of an upfront piece of work before getting to that point. Okay, so the next step is, can we simulate changes in the variables that are important to the system? So in the case of salmon, can we simulate changes in flooding, changes in peak flows, or changes in summer flows? How can we do that, and on what scales do we need to do them? Okay? So what I really want to emphasize is here is that I think it's worth thinking critically about, do you need to go beyond what the global models say? We talk a lot and sort of are very cognizant of the fact that the models are low resolution, but many processes are sensitive to changes at low spatial scales. So is your process sensitive to local scale variations, or is it enough to use large scale variations from the model? That, I'm going backwards here, tells you a little bit about whether or not you need the downscaling or not. Another point to make is that models produce more results than just temperature and precipitation. There may be other variables that they simulate accurately that you could use, and if they don't, there may be other variables that indirectly relate to the process that you're interested in, right? So it's worth thinking critically about this step. Just a little bit about downscaling. So this is an example over the state of Washington for warming mid-century, showing statistically downscaled projection on the left and dynamically downscaling on the top right. So there's these two approaches: statistical is an empirical approach, and the dynamical using a regional climate model. They're better for different things. A dynamical model, if you have multiple variables conspiring to make the change that you're interested in, you probably ought to use a physically based approach where the interactions can be modeled. If you've got a more simple system or sort of limited knowledge and it's exploratory, you want to use statistical. And then the big caution, and this sort of goes back to the idea of thinking critically about whether or not global models are enough, is that, I think one of the dangerous things about dynamically downscaled data is that it looks so good. Right? And so, for instance, this is just from one global model, and actually it's not really representative in terms of the mean warming for Washington of what the other models are saying. So that's a concern with downscaling. Are we just getting prettier pictures but not actually more information? Okay, so the last one, and I think this is one where we really get into navigating this whole array of scenarios that we have available and culling the list into something that's a little bit more manageable for analysis. So what do I mean by scenarios? Here I'm talking more broadly about not just scenarios of greenhouse gas emissions for the 21st century, but also different global models, different approaches to downscaling, different impacts models potentially. So I think really what this is about is deciding what your criteria is in terms of risk. Are you risk tolerant, in which case really you just need a middle estimate, maybe in order to make some initial plan and then reevaluate in the future? Are you risk averse, in which case you want to look at a worst case scenario, or do you want to sort of look at what's the most robust decision to all scenarios, right? So I think there are really three important considerations here when you're thinking about this. The first is greenhouse gas emissions scenarios. So this is showing the trajectories for different greenhouse gas emission scenarios. These are sort of what-if scenarios for future emissions of greenhouse gases. And this is showing the new set in the colored black and blue and red lines, along with the dotted lines of the older set that we've been hearing about in past years, right? So really two important points to make here is you can ignore this completely if what you care about happens before 2050, because warming up until then, roughly, is not is more dependent on past emissions. We've already committed ourselves to a certain amount of warming than future emissions. The other point is, just as an aside, there is some correspondence between the old and the new ones. They're not exactly the same, but some correspondence. Natural variability, this is the opposite. This is much more important if your decision is near-term than long-term. So what do I mean by natural variability? These are these sort of random fluctuations in climate. This is showing historical and future for Seattle, the continental US, and the globe. And the point here is that as you look towards greater and greater specificity in location, so Seattle versus the US, and you look at what the really warmest model runs show versus the ones with the least warming, there's quite a spread, right? And that spread is largely natural variability. One more point about this is there are processes that are going to be more sensitive to long-term fluctuations, some more to year-to-year variability, so it depends on what your focus is, right? If your focus is on a variable that's sensitive to year-to-year variability, then it's going to be important to use single model runs rather than averages, because the averages are going to smooth out that variability. The third consideration I think is important is global models. So global models are different representations of the climate. They don't span the full range of our uncertainty in how the climate will unfold over the coming century, but they're our best estimate for the range. So if what you need to do is get a sense of that range, this is an example, a more concrete example of that contour plot that I was alluding to or showing a schematic of earlier, where this is showing change in annual precipitation against change in annual temperature. And then these contour lines are changes in summer stream flow as a consequence. So you could imagine these numbers are different model projections. You could pick out the ones that span from worst to least consequences. Okay, so really my big take-home point here is that it's context-specific in terms of thinking about climate impacts and making decisions. So we need to combine these sort of top-down climate impacts data sets with a bottom-up assessment of what are the sensitivities to climate change and what are the information needs, right? And I think it's really worth thinking about that critically. And I've summarized some of the key considerations there that I mentioned.